Up here and share my screen, and we'll go ahead and get started today. And again, up front, two handouts today. One is actually stapled together and one did not get stapled together. The one that is stapled together, the way to find that electronically is that's the notes.pdf file in our topic for recursion folder. And the one that did not get stapled together, that is scrolling down a bit more. There's a link right here where it says more runtime analysis. This is a printout of the official Python documentation for the time complexity of their different containers. So I've printed that out for you so that you'll be able to use it on the quizzes, but this is the official Python source for that. Again, two handouts today. One did get stapled together, one did not get stapled. It has 2 sheets of paper in it, and make sure that you get both of those sheets. Today in class, we're going to be, maybe before talking about today, let's remind ourselves how we finished up last time, that we started talking about all of this counting things and counting things manually, getting exact numbers about counting things. And then we started talking about big O notation and this theta and this omega and how we can use those as tools to make the counting simpler for us, because we don't actually in practice need exact numbers on when we're comparing algorithms. And this asymptotic notation is another word for the big O notation. This asymptotic notation is going to be very useful for us when we're comparing algorithms against each other. So today in class this week, there's sort of 3 topics that are all very closely related that build off of what we've been talking about. We're going to see this idea of recursion, which depending on where you took your first intro programming course, you may or may not have been exposed to that yet. Anybody who took CS40 with me, we have not talked about that because the main purpose for recursion, other than torturing like CS5 students, the main purpose of recursion is for runtime analysis. Nobody uses recursion except when they want to use it as a tool for better runtime analysis. And so that's why we're introducing it now in the context of this more runtimes. Our motivating example, the thing that we're building up to this week, is something called binary search. And with binary search, we're going to see how we can make and prove that we'll be able to find information really, really quickly inside of a container. And in particular, we'll be talking about how when you go, or one example of binary search in practice that you've all benefited from is that when you go to google.com and type in a search query, and the way that Google is able to search the entire internet in just milliseconds all boils down to this binary search algorithm. So that's what we're big picture talking about today. A couple of quick announcements before we get into the new technical material though. The first one is that, so the HTML validator homework, this is our homework from 2 weeks ago. My solution to that, I've posted that online now if you would like to see it. You can click this link and go take a look at what my code looks like. Not required to, but if you're interested in just seeing how I solve these problems, that's available. And in general, it'll probably be about a 2-week delay between on all these assignments when you submit it and when I finally post the solution, just to ensure that everybody's had a chance to complete the project before I post it. Another announcement, so about the word ladder, that's your homework that is due tomorrow at midnight. Many of you probably have discovered that it is a hard problem. I think it's a hard problem. In my opinion, it's the second hardest homework you'll have in this course. So if you can get through that one, then things will be good. If you can't get through it, then it's not the end of the world. Though most of the other stuff will be significantly easier. It's not to say that they'll be easy, but they will be definitely easier. And I've tried to time this homework in particular so that it did not, so it came before most of people's midterm exams. So you can really like focus on the homework this next 2 or 3 days, and then the next weeks will be a little bit lighter. You can focus on your other classes for a bit. Another quick note about grades in this course, though. So most of the grade that you'll have in this course, about 80% of your final grade, is going to be based on these projects. And so while my goal is for everybody to 100% solve all the problems, historically that doesn't happen. And what ends up setting apart people's grades from an A to a B to a C is how many of these projects you're able to get. Again, not huge like exams in this course. Your grade's not determined by these exams that you'll have just at the end of the semester or in the middle of the semester. It's really these projects and getting these projects done that will determine your grade. So again, the goal, my hope is that everybody completes all of them, but that's not my expectation. And if there's projects that you can't complete for whatever reason, then that's 100% okay. If you tally up all the points in the class, then the word ladder will end up being worth approximately 5% of your final grade. Any questions administratively? Yes.
So I think you might have said this already, but just for clarification, so for instance, for word ladder, when the grader, I don't think it's a grader, but whoever is determining the grade goes to look at high and puts on the that we're passing all the tests, is that an automatic 100?
If you pass all the tests, automatic 100. Yes. And then if you don't pass the tests, that's when the grader will go in and look in detail about how many tests did you pass and calculate out the grade that way. Currently, I'm the grader for all of these assignments. There's a CGU student who's been traveling who, when she gets back, will take over for me grading the assignments. Yes. Question is, what's going to be the hardest homework? It's on something called AVL trees, which is just a meaningless term at this point. So it'll be towards the end of the semester. But again, I will try to line that up so it doesn't overlap with the typical exam time periods. So you can focus in on that. Yes. Project homework synonym, yeah. Good questions. Any other questions? Anything administrative? Okay. So again, the main new material for today is going to be this recursion and runtime analysis based on that. Before we get there though, I want to talk about some debugging tips for working on this homework assignment, the word ladder assignment, or future assignments. I'll try to incorporate these throughout the semester as we go. So in order to do this, I'm going to switch over to the terminal here. And I have two terminal windows open, and they're both in my word ladder repository at this point. When I'm working, I always have my screen totally filled up with terminals or Firefox if I need to be referencing a web page somehow. And one of the things that I often notice is that students have your font really small, and everyone I see who has small size font, their heads are just way too close to the screen. It's going to be, when I say hurting your eyes, I don't mean damaging your eyes. I just mean it's going to be distracting you from actually thinking about your programming problems. And so I definitely recommend everybody I've seen, your font's too small, increase your font size, and it'll make programming a little bit easier. In this case, when I increase my font size, you can see that my prompt over here is taking up basically my entire screen over here. It'll be really hard to start typing commands. So I'm going to switch my terminals to be vertically separated like this. And now I'll have a lot of space to actually type things out. You really should spend a couple minutes finding a layout that works for you on these assignments that is going to be using all of your screen real estate productively. So whatever that is for you, you should spend some time to actually do that. Here, so we have these files right here. They're both in the same folder, have access to the same files. And very common workflow is to have in one of these terminals to have Vim open with one of these the Python file that you're actually working on, and then down in the other terminal actually run the Python commands. I still see a bunch of students using just one terminal and going back and forth between Vim and the terminal this way. And if you're doing that, then you can't see at the same time your the error messages that you're getting and the code, which makes it really hard to fix what's going on. So having these both visible at once, super, super helpful. Down here, if I run Python 3-m pytest, you can see that I have a whole bunch of error messages going on down here, and it's going to be hard to really start getting a sense of, I don't know, what's going on. What do I need to fix to get my program to work? The first things in all of these assignments that you want to focus on is whatever the helper functions for the project are. So in this case, there's 3 of these different functions, and you should always think about like which functions depend on which other functions, which are the helper functions, and start with the helper functions. In this case, it's sort of arranged like bottom to top, the simplest functions on the bottom, and the more complicated ones on the top. So I would definitely recommend starting with the adjacent and the verify word ladder functions before going on to the top one up here. And in particular, these functions down here, adjacent and verify word ladder, are going to be required in the test cases for word ladder. So another thing that I like to do inside of Vim is I like to have multiple files open at once. In particular, I like to have the Python file I'm working on, plus the test cases file that I want to know how it's going to be evaluating this code. In order to have multiple files open at once in Vim, the command is :tab-e, and then the name of the file that you want to open. In this case, it'll be tests/test_main. The tests folder, so down here on the bottom, in this tests folder, is the test_main. So I'll open that up here. And now I can see the test cases in this tab. If I want to go back to the other tab, GT switches between tabs. The mnemonic for remembering that is anytime you're doing a movement in Vim, or there are many movements that start with G, G for go, and then T for tab. So go tab, go tab, go tab, switching between these tabs. And then up here, just looking at these test cases, I can see that the test cases actually start with the adjacent functions, and then they'll move on to the more complicated functions. You can see that a lot of these test cases are rather complicated things, and maybe sometimes it's useful digging in to figure out exactly what the test case is trying to do, but you're never required to dig in and try to fully understand these test cases down here. Any questions at this point? There's a question? Yeah. Question is, in Vim over here, how do I go back and forth between these tabs I have open? GT will go back and forth between them. And you have to be in normal mode for any of these movement commands to work. So after I get these adjacent and verify word problems implemented, then I can start on the word ladder problem itself. I think most people, I mean, they're not necessarily trivial things to implement, but they're much, much easier than the word ladder. So we'll spend most of the time thinking about how would you debug this word ladder function. In order to do that, so down here, I'm currently in my master branch. If I run git branch down here, you can see that I have 3 branches inside of this, this repository. The solution branch contains the actual solution. The master branch is where I'm at right now, has nothing inside of it. And then this checkpoint branch will be somewhere in between. I'll run git checkout checkpoint like this, and you can see it's changed to the checkpoint branch. And over here, if I'm in the wordladder.py file up here at the top, if I'm going to press Shift-G right now to scroll down to the very bottom, and you can see that this adjacent function has nothing inside of it still. Scroll down to the very bottom, there's nothing inside of it. When you switch branches or do something in the terminal that affects the contents of a file, by default, Vim does not automatically load those changes. In order to make Vim reload a file, the command is :E. E here is short for edit, so we want to re-edit the file, :E. I do that, and now you can see it's made some changes up here. The file is larger, and here's the solution at this point for the adjacent program right here. If I come down here and actually run the tests, if I do something like Python 3-m pytest like this, then you can see that there's a handful of passing test cases, still a handful of failing test cases. And if I scroll up a bit, you can see all the failing ones are specifically now related to the word ladder function and not to these adjacent or the verify word ladder functions. So again, the key thing in Vim here is that anytime somehow a file is being changed somewhere else, :E will reload that file so that you can have access to it again. Down here on the bottom, every time that I do, we can see that my little scroll bar here is getting pretty filled up with a whole bunch of junk. So I'm going to just reset my terminal down here again. I'm never going to need to go back to any of that stuff. So resetting it, clear all that away, clear my history so that I can just focus in on what I want to be working on right now, one thing at a time. And let's just Python 3-m pytest again like this. And we can see, okay, so there's 16 failed test cases here. How do I decide which one I should be working on? Again, like one thing at a time. Let's focus in on just one thing and work on just that one thing. If I scroll up, there's a lot of things to take a look at here. And again, I want to focus in on just one thing at a time. The -X flag will stop PyTest immediately after it hits the first failure. So here now it's saying there's only one failed right here. And that's because I added the -X flag. So now when I'm scrolling up, I know exactly what's the one thing that makes sense to be working on because it's this failure right here. The first failure to found. And now when I'm trying to work on this failure, I don't have to like go through all of these 16 failed test cases and try to scroll up and was I working on this problem or this one up here trying to fix it. So just one at a time, always narrowing yourself down, narrowing the things that you have to think about. One of the key, again, I've said this a bunch of times, but one of the misconceptions that students have is that by just like somehow being really smart or being able to keep a lot of things in your head at once, that's going to help you solve these problems. And really, that's not the key thing that separates out the more successful from the less successful students. The thing that separates the more successful from the less successful students is getting these tricks down that let you focus in on just one thing at a time so you're not distracted by all these other things. So that you don't need like the big galaxy brain to figure out what's going on, but let the computer do the work for you to tell you what you should be doing next. All of these things too are summarized in this little debugging tips section. And so hopefully at the end of our going through this, each one of these bullet points here will make sense. And you can use this as a reminder while you're working what things to work on and to do. So that was this -X here, stop after the first failed test case. Any questions at this point? Yes. If you're getting error messages, then I'll have to take a look at that one-on-one about what's going on. Okay, so now we can focus in on just this one test case right here. And we have to think about like, okay, what's going on with this test case? How can I actually read this and understand the output here? The first thing the general strategy for understanding any error message is starting at the bottom and reading to the top. And doing that, we can see that what's happening here, this error message is actually happening inside of our verify word ladder function. It's actually happening inside of the verify word ladder function. And what's tempting here is to think that, okay, maybe this means that my verify word ladder function is not correct. But if we have run the test cases on verify word ladder, if we've ran these test cases and they're passing, this should give us good confidence that our verify word ladder function is in fact correct. The fact that we're getting an error inside of verify word ladder does not mean there's a problem in verify word ladder. What's happening here is, if we scroll up a little bit more, here's the test case itself. This is right here's the test case itself that is currently failing. In this function, it is calling the word ladder function right here to get this ladder, and then it calls the verify word ladder function right here. And when we call verified word ladder, if we get some sort of really bad input into this function, then this function will throw an error. So the fact that we're throwing an error on verify word ladder right here, and we know we're throwing the error in the verify word ladder function right here because it's showing us the exact line that's causing this type error right here. We know we're getting this error in verify word ladder, but it's not a problem in the verify word ladder. It's a problem in the input to the function. It's a problem in this ladder right here. It's a problem that word ladder itself is not giving us the correct output. If we look at our word ladder function, look at the word ladder function right here, you can see there is nothing in the implementation of word ladder. So this is like having just return none. By default, when there's no return statement, it just returns none. And so this word ladder right here, rather than giving us the list that we're expecting for our ladders, is sticking none inside of this ladder variable and passing none to verify word ladder right here. When we do that, we get this type error, object of type none type has no length. That the ladder was the input to this function, and we're trying to take the length of a none, and so we get this type error of none type right here. So again, the key thing here is just because we're getting an error message, looks like the error is inside verify word ladder, and in fact, the error is being raised inside of verify word ladder, does not mean the problem is with this function, but we have to understand how this function is being called in the test case and inspect the input to the function itself. In this case, the problem right here has two words that are we're starting at the word stone and ending at the word stone. And this is something that we don't even need to really think about in order to implement. We can just have a simple if statement of something like if the start word, and I forget exactly what, yeah, there we go. If start word equals end word, then we can just return start word like that. And so now the ladder that we're getting in this case, we have our start word and the end word, they're the same thing. The ladder that we'll get is just this list that has just that word by itself. And so now we're not going to be passing in a none value right here. And the length of that will in fact be equal to 1. So I think it will pass this test case right here. If we save that, come down here, up arrow, rerun it, then we can see that we're getting these extra things passed, but now always will be one failed. Whenever you have the -x flag, it'll always be one failed. And if we scroll up, we can see that it is in fact now a totally separate test case that is failing, stone and shown. So we had stone to stone correct, and now it's stone to shown that is incorrect. This is a more complicated example. These are not the same words anymore, and so we can't just have a simple thing like this to fix the problem. We'd have to go back and check out that pseudocode and start implementing it. One of the key things about the pseudocode here in the word ladder. So again, there's lots of details in the pseudocode here that are intentionally hidden from you all that you'll have to figure out for yourself. But one of these is this line for each word in the dictionary right here. This word dictionary, it's a little bit ambiguous. What exactly is it referring to? And you're supposed to be able to figure out that there's this file up here, dictionary file, and that this dictionary file contains the dictionary inside of it. I'll go ahead and :tab E, open up this file right here. Words, 5.dict. And so here's all of the 5-letter words contained in the English language. And so that's what we're using to work with here. In order to actually use this dictionary file, though, we have to somehow load this file and get access to it. There are no test cases inside of the test main file over here. There are no test cases related to doing this. And so what's the right way for me to think about actually going through and testing that? Well, I should actually run this function sort of interactively and figure out what's going on. So if I come down here, let's add something like print dictionary equals an empty list. We'll use my @p right here to print that out. And then let's just actually call this function word ladder with stone to shown like this. So I'm calling the function with this test case that I'm trying to investigate, but I'm not even feeling like I'm ready to investigate this because I don't even know how to access this dictionary yet. But I can call it like this. And again, up on the top, save that. Down here on the bottom, Python 3 word ladder. And now this is going to let me, by calling the function right here, I can just focus in on getting this dictionary part correct, printing out any debug information that I need before going back to the test case itself. And in this case, I'm going to have to open up the file. And it's not something that we've covered in this class. My expectation is that you've seen something like this before, but with open dictionary file, is that what the variable was called? It is dictionary file as f f.read. Let's do text equals f.read, text @p like this. Made some changes. Anytime I make changes, I always just check to see, are those changes doing what I think they're going to be doing before moving on and trying to do something with those changes. So I've just loaded the file here and read the contents of the file and then printed out the contents of the file. I didn't try to like process the file in any way in one go. I wanted to test first that I was able to open the file and read from it before actually trying to extract the words from here. But now that I have this, I can try to extract the words from here using any of various techniques of converting a string into a list of words. And then, so convert string into list of words, and then I'll print it, print the results, make sure that those look like a reasonable thing, like I have a reasonable string dictionary here. And then after I have that, then it makes sense to, and I verified that in my terminal down here going back and forth, then it makes sense to come back here and start thinking about the rest of this pseudocode and how to get that implemented correctly. So yeah, key trick at this point is that you don't have to try to test your entire function at once. You should test small subsets of your function as you're working. And you can do that by just calling the function directly and then running your code inside of Python down here in the terminal. And then once you have that working, then you can go back to the test cases. But you don't have to stay just in the test cases the whole time. Any questions about any of these debugging strategies? Okay. None of these sort of debugging strategies are things that you'll be explicitly like tested on at any point or evaluated on. But the better habits that you get into while debugging, the better sort of workflows that you get into, the easier all of these subsequent problems will be. Last little note down here. So the test cases that we have for this particular function, they're a little bit slow. My solution takes about 8 minutes to run normally. You can speed things up if you install this version of PyTest. You can add this -in4 command right here, and that'll say run things in parallel with 4 different processors at once. The way that looks, I'm going to :QA, exit out over here. I'm currently in the checkpoint branch right here. Let's check out my solution branch for a second. This is something that a number of you have run into at different points. That I've made changes to my word ladder.py right here, and I can't check out the solution branch because if I do that, the changes to wordladder.py will be erased. And so Git doesn't want to let you do that by default. In order to get through this sort of problem, you have 2 options. One, you can run git add and git commits and commit these changes to this branch so Git remembers them. Or if you don't want to remember them, if you want to forget them, then you can run git checkout, then the name of the file. And this will erase the contents of this file, erase your changes going back to the previous stored checkpoints. So previously, we've only done checkpoints, we've only done checkouts on branches and commits. But if you do a checkout on a file name, then it will go back in time on that file name. Say that reverts the file. Run that, git status, nothing's there. If I reopen that file, wordladder.py, scroll down, you can see there is no contents of this function anymore. We're back to the checkpoint branch, close out of that. And now I can run check out the solution. You'll notice up here when I check out the solution branch, here it says solution in my prompt. On the bottom down here, it still says checkpoint in my prompt. That's because the prompt gets displayed only once and never gets updated. But if I just hit enter down here to update my prompt, then it'll be in the solution branch like this one up here. And if I were to run the Python tech-m PyTest like this, oops, Python 3-m PyTest, you can see this is taking a little bit long to run. Control-C, stop that. Python 3-m PyTest with this -in4. You can see it's just made a lot of faster progress down here running these tests in parallel. It's ran a lot more tests so far. And if I let this run for 5 minutes, it would eventually pass them all. So this -in takeaway here is that this -in can speed things up. Probably not something that you want to do like while you're working on an individual test case, but once you think you have everything working and you're ready to remove the -x flag or this last failed flag from your PyTest command, you can add the -in4 to speed things up. Yes. Yeah, question is, how does the -x interact with passing all of them? And the answer is that, yeah, it'll run through them all, and then it'll tell you that it passed all of them as if you didn't have it there. The -x only affects things when you have a failed test case. I guess actually, I don't think I mentioned this one or spoke about it out loud. The -- last failed skips any tests that were successful. And so if you add the -- last failed, it'll skip over the ones that you already know are passed, and you combine that with the -x to just focus on the one that's failing. This one is the most useful from like the output that it gives you perspective. It simplifies the output. This one over here will just make it run a little bit faster. Good questions. If anybody has any more questions about these sort of debugging tips, or you're running into any error messages, happy to take a look at that after class, during office hours, or during the lab time with you all. What we're going to do for the rest of today, though, is start going over this more runtime analysis and get into this idea of recursion. Again, the motivation why we're talking about this is this problem of search. It's somehow like the most fundamental or important problem of computer science. And there's two reasons for this. The main one is just that it's so ubiquitous and important. Like every time you go to Google, they are doing this search problem and running binary search internally. So it's used all the time. Very common for interview questions because of that, because every company is using binary search internally in hundreds of different locations. And so they want their employees to have a full 100% working grasp of these different search algorithms. The other reason that this is so important is it's going to really highlight some issues about runtime analysis and complexity for us. So we're going to take a look at two different algorithms for search, sequential search and binary search, and we'll see many different ways that we can implement either of these two high-level ideas. But what we'll see is that this sequential search algorithm will have what we call this linear runtime over here, this theta in. We call it linear because it's just an in over here. It's like a straight line. And the binary search is going to have this logarithmic runtime of theta of log in. And in class, we'll talk about the actual math of proving this analysis. And then again, in your lab this week, you'll go through and run some experiments to measure just how much faster is this login than the linear time here. In order to do this, we'll go through this time complexity notes sheet and the notes.py file that I printed out. Again, this time complexity sheet, this is the official documentation for Python's time complexity of its different containers. The document here is unfortunately, I think, not very good. It's kind of confusing how things work. So we'll go over this. You should have it out in front of you so that you can take notes on this. You don't have any quiz practice problems yet related to runtime analysis, but you will be having quizzes on this in the future. And so having these notes in a good shape for future quizzes will be useful for you. And so with that, that's our one file to have out. The other file to have out, again, is this notes.py right here. And it has a bunch of functions inside of it, starting off with sequential search versions of functions, and then a binary search section at the bottom. All of these functions are also available inside of the topic 4 folder, not as a PDF file. So here's the PDF file, but it's also available as a Python file right here, the notes.py. And I'm just going to verify for us for a second that the notes.py file is correct, that we're going to be passing all of those doc tests. Again, anytime you see a new function, the absolute first thing to do before you think about runtime, before you think about anything else, is to verify its correctness by running the test cases. So here, this notes.py, like this. This is the same content as your PDF file. And if I run python 3-m doc test notes.py, typing it correctly, there we go, notes.py, you see we get no output down here indicating that it does in fact pass all of those doc tests. So our implementations are all correct. Now that we know they're correct, we'll think about what exactly are they all doing and what is their runtime and how do they compare to each other. There's inside of this file, inside of this sequential search section, there's many different functions, and each of these functions is labeled where the first part of the name is sort of the high-level idea of the algorithm that we're implementing. And the second part of the name over here is whether it's an iterative algorithm or recursive algorithm. So ITR stands for iterative. And then do this REC right here, that stands for recursive. And we haven't talked about what recursive means yet. I'm just saying that REC stands for recursive. And for each of these functions, there's multiple versions. So here's one without a number. This is a second version right here. And then there's multiple recursive versions as well. We're going to take a look at these sequential ones, these iterative. Anytime you see the word sequential and iterative, those are just synonyms of each other. They mean the exact same thing. Sequential and iterative are synonyms. I'll use them interchangeably. Anytime you see, so we're going to go over the sequential versions of these algorithms, understand their runtime, understand how it applies to that Python documentation, and then we'll go through talking about what is recursion and how is it different, and why might you want to use recursion instead of iteration. Any questions about the setup of where we're going? Okay. So here, in this algorithm, again, it's sequential or iterative. We can see there's a for loop right here. Anytime you see for loops or while loops, that tells you that the algorithm is probably somehow sequential or iterative. So for or while. So the sequential, iterative, also sort of synonyms for loops. And the idea of the sequential search algorithm is that we have a container over here, this XS. Our doc tests have it be lists, but we've seen the deck example. It could be a deck as well. It's just not tested against that. Some sort of container, and then this Y value over here is something that we're trying to see, is it inside of the container or not? And so here, this sequential search iter, we have the number 2 right here. We look through all of the entries in this list. We can see that the number 2 is there, so we get true. In the second example, we have the number 6. The number 6 is not contained in this list, so we get false. The idea of a very simple way of implementing this is we loop over each of the entries in this input container, in this case a list in the input container, check to see is the value of that entry equal to the value that we're looking for, and if it is, we'll return true, otherwise we'll return false. And based on this, there's the first concept for us to talk about is something called the worst case versus the best case of an algorithm. The best case runtime of an algorithm is when our container over here and our Y value are structured in such a way that the program is going to terminate really, really quickly somehow. In this case, the best case algorithm, or the best case Y value, for this list is equal to 1. Because in the event that Y is equal to 1, we will immediately stop as soon as we hit this, this 1 value right here. Our list right here, our iteration right here is going to start going through all of these entries, but because down here we are returning true, as soon as we find something that is equal to our value, then we're going to instantly stop. So this one will stop after only a single iteration. This is usually, so we call it the best case because it's the best case, but usually not what's going to happen. Usually when we're searching for things, we're not going to be searching for something at the very front. And so usually what we're actually interested in is the worst case analysis of an algorithm. In the worst case, we're not going to stop early, so we're not going to hit this return here. We're going to have to go through the entire for loop, and then we'll return false down here. So the worst case is when Y is not contained in XS. We must finish the whole for loop. And in this case, that's going to take n iterations. Again, whenever we have a container, we typically use the letter n as the size of the container. So here we have XS. We're thinking about the runtime of this algorithm in terms of the size of this container XS right here. And we use just in as the shortcut for the size of that container. So the best case, this is going to take only one iteration, and in the worst case, this will take n iterations. Typically, we care about the worst case analysis of runtimes more than the best case, because if we know that the worst case is small, then we know that all possible things, the best case is going to be small. No matter how we run the algorithm, we're going to be fast. And so typically, this is what we always care about. In this class, this will be the only thing we care about. What we care about in this class. If you take subsequent computer science classes, you'll talk about other types of analysis that are potentially more useful, but we'll focus on the worst case here. Here I said that it's going to take n iterations to complete this for loop. And we're going to take a look at this next iterative algorithm 2 down here, and we'll also see how many iterations does it take to complete this for loop down here. I want us to be careful at this point, though, that we're really talking about the number of iterations of this for loop, and we're not yet fully talking about like a runtime. We're going to use this as a stepping stone to talk about the runtime and compare the runtime of these two algorithms here in a little bit. But right now, we're really just talking about how many iterations of this for loop are we going to have to run through. In this case down here, the difference between iteration 2 and iteration 1 is that we are looping not over the values of the list. For x and xs right here is the values of the list. Down here on line 10 in the second function, we are iterating over the indexes instead of the values. And then on line 11 right here, this is doing the lookup operation instead of just getting the value itself. This doesn't affect the total number of iterations in either the best case or the worst case. The best case is still exactly one iteration. If xs at position 0 equals y, then we'll return true. And the worst case is still exactly in iterations. But we'll see that this will have an impact potentially on what our actual runtime is. So number of iterations. Is the same, that the best is equal to 1, and that the worst is equal to n. And this blue is about this second function down here, this stuff up here about the top function. In order to go from the number of iterations to the actual runtimes of these functions, that's where the notes on the time complexity from Python is going to come into play. And we'll need this sheet right here, and we'll also have to start talking about what is the actual type of the container over here. We'll start by thinking of these containers as lists, and then we'll move on to thinking of them as decks, and we'll see what the difference is between the two situations. When we are talking about the actual runtime, now we need to think about for each of these operations, what we'll have to look up over here in our Python documentation, what is the runtime for that operation for the particular container type that we're looking at. I'm going to use in blue up here for a list. And here, this operation right here is what's in the documentation over here is the iteration. Iteration right here. Anytime you see this iteration in the time complexity chart, that refers to a for loop happening. So this is going to take time O of n in order to do this, this iteration line right here. The if statement down here, these two lines right here, They don't reference anything about the container itself. The XS variable is not mentioned in either of these two lines. XS is not mentioned, so they won't affect the runtime in any way. Anytime we have a line in our code that does not affect the runtime in any way, we will always say that those lines of code are O of 1 in their runtime. O of 1 in their runtime. Up here, we have O of n. Down here, we have O of 1 or constant runtime. And this O of 1 is going to happen in total times, once for each iteration through this for loop. So this O of 1 will happen n times, giving you O of n again. And so this whole thing will remain as O of n overall. It's a little bit scrunched in here. But yeah, just the key thing is that the stuff inside of here is constant O of 1, happens in times, multiplying those together gets you the O of n linear runtime. This O of n is an upper bound, so it's not the theta, not the omega, just an upper bound. So it is true both that the best case runtime and the worst case runtime is O of n. In the Python documentation over here, they don't, they're not careful about distinguishing between the O's and the thetas, and that's intentional, that these are only the guarantees that they're providing, and it's possible that the iteration could be faster in some circumstances. It's possible that this insert could be faster in some circumstances. So they're not providing lower bounds, they're just providing upper bounds on how slow the operation could possibly be. Again, in this case, there's only one operation here, the iteration, the contents of the list, or the contents of the for loop not doing anything, so the overall runtime linear O of n. If you have questions, we'll do this second one is slightly more complicated, so it might make the first one make a little bit more sense. Down here, again, for I in the range of the length of XS, this is an iteration operation. It's going to take the O of n time. But there's a couple of other operations inside of here as well, like this length operation. And this length operation is something that we'll just have to compute once. And but we still have to know what is the runtime of computing the length of a list. Let's come down here at the bottom. Get length is O of 1 time or the constant time. So that is O of 1. Again, one of the confusing things about the official Python documentation is that they use their sort of, I don't know, just generic English language descriptions on what's going on over here. This get length corresponds to the length function itself. And in this case, it's, I don't know, sort of obvious that length and get length correspond to each other, but it's not as obvious as I would like. I wish they had just actually used the word len right there so that I know that the len function takes O of 1 time. You have to do a little bit of thinking here to know that get length here corresponds to the len function. Down here on line 11, this indexing operation, subscripting operation, is now happening based on the container. Up here on the line 11 of the previous problem, we were comparing the values of the container, not like totally ignoring where those values came from and just comparing the values themselves. Down here, we are using the subscripting operation, so it is still accessing the actual list. If we come over here, we need to figure out where is the indexing or subscripting operation at. It's not that, not the in, not sort, slice, get slice, no, delete item, set item, get item, there it is. So it's not obvious that get item corresponds to the square brackets, maybe, but get item does correspond to the square brackets. Set item, this is a little bit confusing. Set item will also correspond to the square brackets, but in different situations. If we have XS square bracket 1 like this, something equals to that, this is the get item, where the subscript is on the right-hand side of the equals. If we had something like XS of 1 equals X, that's the set item. So the set item and the get item both corresponding to square brackets. It just depends on which side of the equals sign you're on. In this case, it doesn't matter for the list that they're both constant operations, and but for other data structures, it can matter. There's another thing that I've glossed over so far is the difference between the columns over here. We have the average case and the amortized worst case. It's always the worst case column that you'll want to be looking at the values for. And for the list, it's the same for the average and the worst case, but for some of the other data structures that we'll get to later on, it'll be different. So it should be the worst case columns that you're extracting these values from. And again, the get item corresponds to this O of 1 over here. So we said the get item is constant time. O of 1 right here, constant time. And so even though this has a little bit more going on inside of it, it's a little bit more complicated. The final runtime is going to be the same because we have constant time. O of 1 things happening in the middle. It's happening in times, O of n times for this for loop. And so the overall runtime here is still going to be O of n. We're going to move on to next talking about the deck, and we'll see that with the deck, these two functions will have different runtimes, different runtime guarantees, and so it'll be very important to pay attention to which style of iteration you're doing when you're working with decks. But for lists, we can see that the runtime is going to be the same, whether you're looping over the indexes or looping over the values. Any questions so far at this point? Yes. Question is, O of 1 here, how does that relate to the F and the G functions from our last set of notes? And the simple answer is that, so if we have our graph, rather than appealing back directly to the functions themselves, I'm going to look at or rather than appealing back to the asymptotic notation, I'm going to do things a little bit more intuitively. That a straight line like this is the constant function 1 value here everywhere. And so if our runtime is 0, if we're not doing anything, then 0 is always less than 1. So 0 does in fact equal to O of 1. That is a 0. And that's the big O. I'm doing this at an intuitive level a little bit right here because the actual question was, how do the F and G functions come into play with these runtimes over here? The answer is that we don't actually know exactly what the F function is. The F function is not something that they give us over here. We only get the G value. The G is the thing inside of the parentheses over here. And they're only giving us a guarantee that whatever the actual runtime is, F is the actual runtime. Whatever the actual runtime is, it's just upper bounded by these things. So if we use these values over here, we'll get an upper bound, but we'll never know what the actual underlying function is. Did that answer your question? Good question. So coming back up here, I'm going to delete all the notes that I have here, so we'll be able to redo this with the deck case. Click delete that. And now when we think about the deck, we're going to have to redo, again, all of that procedure. It's not a whole lot of things to look up because there's not a whole lot going on here yet. But redo that procedure specifically for the deck and plug in those numbers, simplify the results, and get what the final runtime is. So the deck here is immediately below the list. The first thing that you'll notice is there's just a lot fewer operations down here that they have listed for the deck. Part of that is because the deck just supports fewer operations, but part of it is because the documentation here is actually just a little bit incomplete, and that's a little bit frustrating. So coming back to our this first function up here, the only thing that really mattered was this iteration runtime looping over everything. And if we come over here, you can see that there is no iteration entry inside of the collections.deck. There is no iteration entry like there was on the list up above. And the reason for that is because it turns out that every data structure that's implemented in this collections library, the iteration is always O of n. And so for every data structure, in the collections library, not necessarily in other libraries, but in the collections library, iteration is O of n, and they're just assuming that you know that to be the case. And so in this case, in this first function up here, there's only one operation that mentions this XS variable, only one operation that we do on XS. And so since it's for every data structure, it's going to be linear runtime. This operation, this whole function will be O of n for every data structure. O n for all data structures. We're going to see that that's not the case down here with this second iteration style right here. Down here, we call our length operation right here on the XS, and we have the subscript operation right here. The length operation, and again, we're working on a deck now. The length operation, let's come over here. Length operation still takes constant time, O of 1. Again, we should be looking in the worst case column here over on the right, O of 1. So that's good. That'll take constant time. And then we have our for loop here, looping over all n values. So that will be the O of n time. And now we have our subscript operation right here. We need to figure out how long that's going to take. And this is another sort of unfortunate thing in their official documentation. But they just assume that everybody knows that in the deck container, when they say it's represented as a AA linked list right here, then they assume that everybody knows that that means that the subscript, whether it's the get or set item, will take O of n time in the worst case. Yeah, so it's unfortunate. It's not listed anywhere explicitly in this table, but the get and the set operations, the square bracket, subscripting, indexing is O of n time in the worst case. And so here, when we have this if statement right here, this is going to be actually O of n as well, whereas previously for the list container, it was O of 1. The key difference between the deck and the list, one of the key differences is that the deck is O of n, in indexing, but the list is O of 1 in indexing. Now, when we simplify these two things together, we'll be multiplying them together because this operation happens inside this operation. This one happens once for each of the times that this operation happens. And so we'll multiply these two things together. And when we do that, we get that this is an O of n squared algorithm. O of n squared right here. And so in particular, the runtime of this function down here the runtime depends on the data structure used for XS. It depends on exactly how this XS thing is implemented, whether it's a list or a deck. We've seen that you get different runtimes, and other container types will get different runtimes as well. Yes. So the question is, are we talking about a list or a deck right now? The answer is that anytime we're talking about the runtimes of a function, we have to specify what container we're doing it on. The first time we talked about the runtimes of these two functions, we talked about it with a list as the input. Now we reset that. We're going through it again, talking about the runtimes with the deck as the runtime. So the question is, isn't this a list? And the answer is that in the doc test right here, it does in fact have a list as the input, but this function, you can pass whatever you want into it. The only thing that determines what the type is right here is the person who's using this function, what type they're passing into it. So in this case, it would be a list that is being passed into it. But if we quit out of this, let's open up the notes.py. If somebody were to just change that and deque, call it like that, then now it's a deck being passed into it. And so the runtime is going to have different runtime properties. For the lab, you hopefully noticed that whether you were using a deck or a list, you were getting different runtime properties on certain functions and not on other functions. And the reason for that is because of this list indexing, or sorry, the subscripting right here, the square brackets. When you do it on a deck, you get really bad performance. So the square bracketing, something that you never ever want to do when you're working with a deck. It'll always get you slow performance. Any other questions at this point? Okay, so the lab this week is going to have you going through these functions and some other ones with similar to how you did last week, and running the actual computing runtimes, and also computing these asymptotic runtimes, and verifying that the asymptotic runtimes do provide good predictions of what the actual runtimes are in practice in terms of milliseconds. So you'll have more experience with this later on in the week. We'll move on to next, very briefly though, is exactly what's going on inside of the recursive versions of these functions. Here, in a recursive function, there are three things that you need for a recursive function. And if I'm going to come over to our class notes and scroll down to here under recursion, the three things that you need for recursion are listed right here. Before we get there, if you've seen proof by induction before, for example, in discrete math, recursion is very closely related to proof by induction. And in fact, every one of the reasons people like recursion is that it's easy to prove that your algorithms are correct using proof by induction. If after this class you go on to take the CS 148 algorithms class, usually taught by Professor Cannon, then you'll talk a lot about using proof by induction to prove recursive algorithms are correct. It turns out that every algorithm can be written either in the iterative way we've seen before using for loops or this recursive way. And the key thing about recursion is that an algorithm is going to call itself. So down here, we can see that on line 1, we defined the sequential search REC function right here. Again, REC, short for recursive. And then on line 14 down here, what makes this function actually recursive is this line. This is what makes the function recursive. Because it's calling itself inside of itself. In order for this to work, this size of the problem right here somehow needs to get smaller and smaller each time. So here, when we have XS up here, if the size is in, now we have a slice down here making the problem size smaller. The other thing that you need for recursion is that what's called a base case, where the program is actually going to stop and decide not to work anymore, decide not to call itself. So in these up here, these 4 lines, this is what we call the base case for this algorithm. Or for this function. And here you can see that in the base case, that if one of these 2 conditions right here returns true, if this returns true or this returns true, then we're going to stop. We're going to return without going into the recursive call down here. And so this is what's going to cause our function to actually stop and terminate. Again, these 2 things, the recursive call with the problem size getting smaller, plus a base case down here, this is what you must have for your recursive functions to work. Your next programming assignment, your next homework is going to have you implementing recursion, and the most common cause for mistakes is the slice right here, not making the problem smaller, or not having a base case up here. We'll get more walk through this example here next time, but I want to, before we get there, take a look at these cartoons that we have up here at the top. There's a lot of programming jokes related to recursion. And so here, this top one, Winnie the Pooh, what's recursive about this is that, so your readings start here from the top left, down here, oh no, you're eating recursion, and you start over again down here. It's the same comic going on and on and on forever. And it's really easy to have your recursive problems accidentally get into these infinite loops. And we'll see next time that this base case is what's going to stop you from getting into these infinite loops. Another really common thing in computer science is people having what are called recursive names for their projects. The GNU system, GNU, is a very famous open source project. All of the like the ls command and the cd command, all of these things that you've been using inside the terminal, they're all part of this GNU project. And GNU is an acronym, recursive acronym that stands for GNU's Not Unix. And so this is an actual, this comic is a transcript of a court case where a lawyer was having to explain this recursive acronym to the judge over here. And so he's asking, did you say the G in GNU stands for GNU itself? And the judge saying that doesn't make any sense. And that's what recursion is. It's not going to make any sense for a while until we get the hang of it here. But we'll do that next week or next class session. We're out of time for today. And happy to stay at class, answer any questions that people have. Again, quiz on the memory management stuff on Wednesday. that is it for today.